not what? It's not differentiable there. So we can't say C implies D, right? But Washington, D.C. is lovely. D implies C implies what? L, always. So if that helps you in your logic, I think it's great. I do want to point out you can reverse these and do a contrapositive if you put the words not. For instance, that's not true, but you can say this in math. Not C does imply not D. You can do that. You can do that. It's called a contrapositive. You can reverse it and put nots. It's actually logic. You ever take a logic course? Oh yeah, there we go. It's logic. It's this idea of logic. You can reverse it and put nots on it. If a function is not continuous at a point, then it is not differentiable at a point. All right, here's my problem. See how you do with this. Can I erase this? Yeah? All right, JVCs, we got it. All right, differentiability of a function. Here it is. F of x equals, I got a piecewise, I made this up. All the other classes taking the quiz. Sitting here brainstorming something. 3x minus 1. If x is greater than or equal to 2, comma, if x is less than 2. Hey, you all are awesome coming out on this Thursday night, hustling through crazy traffic and all that. See? So, this problem won't be on the test Tuesday, but it will be one just like this on the final. So I'm going to give you that heads up. She made it all the way out here. Plus the people watching the video. They're the ones who got stuck and had to turn around and go back there. No, but yeah, I'll put one. You'll see one of these on the final. It's a nice final type of question. Conceptual stuff. But all right. All right, what am I? There's a function. It's a piecewise function, right? That's a parabola. What's this? Aha, so you got parabola, straight line, but maybe it is differentiable when they meet. It'd have to be smooth, wouldn't it? Right? Yeah, the slope from the left would have to match the slope from the right. I mean, you could design a roller coaster like that, right? Something came out like this, parabola, and then you attach the nice straight line right here. As long as you hit the slope perfectly, you're good. True? So that's what we're looking at. So here's the question, you know, which statement is true? The limit as x approaches 2 of f of x exists. All right. Letter B. F is continuous at x equals 2. And letter C, F is differentiable. Differentiable means the function's derivative exists at x equals 2. And it can be more than one of these. All three of these could be true. Only one of these could be true. None of them could be true. We're just going to check them all out, right? Almost like a true-false. Which statement is true? Is this true or is it false? Is this true or is this false? Is this true or is it false? That's what we're going to check out. I'm going to start with limit. How do you check limit? I'm going to check limit. Yeah, we could do that. I was thinking this. Let's check continuity. Right? And if it's continuous there, then it has to have the what? Does that work? So when I say let's check continuity first. Now, do we have to make a graph? No, because he had an idea last class. I like yours. What do we simply have to do to check continuity?
Replace your 2 with that, or x for 2, and we'll solve.
Check
If we're even.
Love it. And when, you know what we're going to do for check continuity? Let's start there. Because it's so easy. Plug a 2 in, plug a 2. They got to match. If they match, continuous at x equals 2. If those y values don't match, it's broken. It's not continuous.
So what if it matches, but it's like it's not continuous, like in a linear
Well, if it matches, it's got to be continuous. If if these two y values match,
Oh yeah, I'm talking.
right? As long as I use that same thing, but now you're under, you go, oh, it might not be differentiable. There you go. And we'll get to that. We'll do that afterwards. Very good. Very good. This is calculus, right? You got functions that are continuous, but sometimes they're not so differentiable there. Yeah, all right. All right, is it continuous here? Check. True. Very good. True, everyone. And we're going to show why. Look, in this case, what's 2 squared plus 1? 5. What's a 3 times 2 minus 1? 5. Y value is equal. These two y's are the same. So, what does letter A have to be? True. If the function's continuous at the point, then the function's got to have the limit exist in there, right? Yeah, it's connected, so of course the limit exists from both sides. I was just curious, we don't have to do a proof, but we do have to know how to get derivatives. Who knows the derivative of this graph? AKA, here's my hint, derivative means slope of tangent. Who knows the slope of a straight line? Slope of a straight line, mx plus b. I'm going to write that here. I'm hearing it. Isn't that a straight line? mx plus b straight line. Which number is the slope? 3. Aha. So what's the slope from the left side? Right? The slope from the left side is a what? 3. True? All right, so I'm going to write this down. Slope from left at x equal to 2. I'm just putting words. You could do this if you wanted to. You'd have to put a little minus there, though. If you wanted to write the math notation, everyone, like a math, like a mathematician, you're like, I don't want to write words. You'd have to write all this and put a 2 here and then put a little in the minus here. But I'm talking about the slope from the left is the value what? 3. Sure. Now, how to get the slope from the right? I taught you this at the end of last class. Remember the power rule?
F prime.
Yeah. What's the slope? How to get the derivative? Do you remember what you can do? Instead of doing it the long way, move the 2 in front, and then we have to decrease the power by what? 1. So let me write that down. So that's slope from the right. I'm going to put a wall. What's the slope? Slope from the left. What's the slope from the right? We're saying it's the derivative. So I'm going to put that word down. You know we're doing a derivative from the right. Just like derivative from the left. Slope from the right. I'm going to use the power rule though. 2 in front. Decrease the power by what? 1. But, what's the derivative or slope of a constant? 0. So this is it. But what number do I have to plug in here to see if it matches? 2. Yep. It's always at that, right there at that value. So I'm going to put, everyone, would you just plug in x equals 2 into this expression? What's 2 times 2?
4.
Are the slopes matching? So what's the answer? What's going on with C? True or false? False. No. Is F differentiable? No. No for this guy. Slope is 3, slope is 4.
How come you took the derivative of x squared plus 1 but not derivative of the bottom one?
Oh, you could do it. Do you want to do it? Because I was thinking we could think algebra. Slope of a line is tangent. Slope of a tangent line. It's just slope. Because remember, derivative means slope. It's easy with straight lines, isn't it? But if you want to do it, what's that power right there?
It'd be 3.
Oh, good. So it'd be 1 times 3 x to a 0. Now I'm going to write that. You get 1 times 3 is 3x to a 0. But what's x to the 0 now? 1. So very good. You can do it every time.
Can we just look at the continuous points and see whether it goes in the linear pattern or?
You could do that. Yeah. But the key is you really, whenever we're talking about that for differentiable, for it being differentiable or not, we really have to focus on that slope right at that point. We have to do the derivatives. Hey, try one more, everyone. This time, just do letter C, okay? Just do letter C. True or false? One more for your notes. There you go. is F differentiable at 2? So I use 2 again. Remember, there's my cutoff 2. That's smooth everywhere except we're running about 2. By the way, if you notice something, everyone, I made sure it was already continuous. I want to point that out. I made sure it was already continuous. Can you tell 2 squared plus 1 is what? 5. What's 4 times 2 minus 3? 5. I made sure it was continuous because D implies C equals L, but not C implies what? Not D. If it wasn't continuous, it's not differentiable. So I don't want to, I want to make sure I gave you something that was continuous. So this is already continuous at x equal to 2. I was just curious if you could figure out whether or not it's differentiable. Slow. Well, this is going to be the same slope, right? What's the slope from the left? 4. What's the slope? 4. What do you think? Parabola meet in straight line, but the slope is exactly what? 4 at that instant. From the left side, from the right side. A little from the left, from the right. I'm sure mathematicians love to just keep writing all that stuff, but I want you to focus on it. It's like, I just got to look at the slope, the derivatives.
Why is the slope for derivative from the right so it's 4? Because last time you did it, you did it 2x and you multiplied it 2.
Oh, you're right. So that was the same thing here. Let me make sure. This was from the right side, right? I'm going to break all this. So this went with this. That's true. That stayed. That stayed the same. This part came from here. But try it. What's that derivative of that function? Well, it's a straight line. So we know what the slope is. It's 4. But you can still do this rule, the power rule. There's a 1 right there. 1 times 4. Decrease it by 1. You get 4x to a 0. But x to the 0 is just what? 1. Or if you wanted to do that, but that's the long way, isn't it? Yeah, we're like, okay, we did that once. We get it. Cool? Awesome.
Is it differentiable then?
Yeah, I'm sorry, I never put the answer down. Yes. Let me get that out of the way. It's sitting on the video going, false. Oh, this is what? This is true. The answer is yes. Yes, it is. And what would this look like, everyone? You'd have a parabola that did what? What goes on it, too? It would hit here, it would hit here, and it would come up like this. So here's the picture. And then right at that point, 2, 5, you'd have it meet this what? This straight line, but it would be nice and what? Smooth. Boom. Smooth. Slope left, slope right there at that point. Right? It's like someone's designing a roller coaster that came down and what? Just went off in a straight line. Have you ever seen things like this? Or water slides like that. The water slide comes down, that's like, but they make sure they don't give you the water slide like this, do they? And then it's like, true? Right. Right. I used to garden Ocean City, everyone. But this is back in the day. I don't know if you were born in 1987. And they just built a slide on the boardwalk. So my guard stand was right off the boardwalk. And it was the first year of this thing. But there's not much room on the boardwalk, is there, for a water park? I don't know if this water park's still there. So they put a slide in. I am not lying to you. It was like super steep slide like this. The catch pool, I am not lying to you, was that long. Let me fill it in with water. I mean, y'all, the first time I saw this, because I worked in a water park years before this, I'm like, oh man, are they asking for trouble? I mean, they're asking for lawsuits and stuff. I mean, this is what I saw. I mean, it was super steep and stuff. And everyone ever got a water slide, you get on your shoulder blades, you bounce like a rock. Yeah, so they're like, no, we'll put a sign up that tells them that. Oh, come on. Everyone, the manager there, he said people were losing teeth. Yes, loose teeth. I mean, they came in and just boom, right into the wall. They bounce up on the cement, cut all up and stuff like that. So they started, you're going to laugh at this, they kept it running, they were trying to keep a business going. So they'd have the attendants that worked there, they'd hold the raft at the end. They'd all stand with raft. True story, I'd watch them, they'd just stand there, so you can pay, back then we got paid like $4 an hour. I was like, $4 an hour, just stand with raft. This is true. I mean, you saw it coming. It's just dealing with, basic physics. It's like, yeah. You gonna let that go? All right. I want to be like Freeman, just keep talking about water slides, right? Hey, on the last thing we gotta do, 2.8, is we're gonna get a function of f, and we're gonna graph the derivative of f. So now we're gonna graph the derivatives. Graph the derivative of f. This is cool. So I'm gonna give you a function f, you and I are gonna get an idea what the graph of the derivative looks like. So let's see, this will be my first one. How about this guy? Graph it like this. Almost like one of those trig graphs, you know? How about this? It's almost doesn't look like one of the trigonometric graphs, like a sine or cosine, y equals sine of x, y equals cosine of x. Let's call this f of x. And then if you can in your notes, I think it helps. Would you, if you have room, right underneath it, let's graph f prime. Because it really helps us stay organized. So right underneath this, we're going to graph f prime. I'll put it in green. F prime of x. We're going to graph that. I'll just keep it nice and all right. We go x-axis, y-axis, x-axis, y-axis. I'm going to graph the derivative. This is fun. If you're curious what I like to do in my exams, on these, I like to do a matching, and the textbook has a matching exercise. I put it for practice. It's one of your practice problems to try out, so it's good practice. See if you can get that one. But in this case, I'm going to graph the derivative. It's not hard. This is what I want you to do. Would you focus on this graph right now and tell me where the slope of the graph is 0? I'm talking like this. If you threw a tangent line to that graph, it would just be flat. Can you give me some spots?